Looking at the IV graph, so for a semiconductor diode or a PN junction. Okay, so remember what we did for IV graphs. Okay, so we have a power supply and we have a variable resistor, or the way it's set up, we call this a potentiometer, so we can call it a variable resistor or rheostat or potentiometer. So remember, the ends of the variable resistor are connected to the power supply and the sliding contact is connected to the main part of the circuit. Okay, we need to measure current. In this case, we measure milliamps. Okay, we measure milliamps. Using a milliammeter, we measure small current. It's small currents for diodes. Okay, right. Generally, we put a resistor in. Okay, in series to protect the diode. Okay, the diode is here, and across the diode. Sorry, I'm going to put this resistor over here over the way. We're just putting that in for the crack, really. Okay, right, and okay, that's it up. And remember, at all times, to get the voltage, you apply the voltage across what you're interested in. So I'll use the red, as we used to do before, and we put our voltmeter across here. And that's fine. Okay, that's it. Right? Right, so basically all we do is we adjust the voltage of this to 0.1 of a volt. We're putting 0.1s rather than ones here. 0.1 of a volt, and we meet the current. 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, and we see what happens. Okay, and what you see happening now. Okay, let's look at this. Look, watch. Plus to the diode. Arrows in the correct direction, so that's in forward bias. Make sure you understand the idea of forward bias, going from plus to minus. You travel from plus to minus. When you get to the diode, the arrow should be pointing in the direction you're traveling. Okay, and you're going from plus to minus. Right, so what we see happening is, okay, when we do it, current, and you write it as milliamps, okay, and voltage. What you find happening is, as the voltage goes up, nothing happens. The current stays at 0 or almost 0. Because remember, the junction voltage hasn't been overcome. There is still an insulation in the depletion layer. No current flows, or very little current flows. Suddenly, the depletion layer has broken down and a very large current flows. Now, it's suddenly, reasonably suddenly, so about 0.6 of a volt. Okay, we see it going like this, and suddenly it goes off like that. So it's quite dramatic, quite dramatic curve, IV graph. Okay, and this voltage here is the junction voltage, and you need to know that. Okay, that's the junction voltage. Okay, that's it. So suddenly this should make sense to you. Okay, if this doesn't make sense to you, go back and look at the notes, go back and look at the previous clip and see, does it make sense. Okay, as the voltage increases until it gets to the junction voltage, there's still an insulation, so you're breaking down the insulation, but there's still insulation, so effectively it's a resistor and it's keeping the current very low. Once the insulation gets completely broken down, there's no resistor left in the circuit, so suddenly the current gets very large. Okay, it sure as hell doesn't obey Ohm's law. Okay, it is not a straight line graph through the origin. Ohm's law is not obeyed. V is not proportional to I, as you know from your other ones. Okay, right, that's it. Now, okay, there's an extra bit. This is the real interesting bit at the end. Okay, there's an extra bit right at the end. Okay, if you want to reverse bias and see what happens, you have to make a series of changes, more than you'd expect. Okay, so let's look at what we do. Okay, now before we do that, let's remind ourselves. Okay, when we put the voltmeter in, we want as little current as possible going into the voltmeter, because effectively it's changing what you're measuring. Okay, because if this voltmeter hasn't got a very high resistance, the current here is less than it should be. The current going through the diode is less than the current going through the milliammeter. So voltmeters works because they have a very high resistance. They take a tiny bit of current because they need to measure the voltage, but that's all. So that only works because the resistance of the voltmeter is much greater than the resistance of the diode. Okay, and then we can assume that almost no current goes through the voltmeter, almost all the current goes through the diode. Therefore, the current you read in the milliammeter is the current going through the diode. Okay, great. We put into reverse bias, we have a problem. Okay, if you reverse this, okay, so changes you're making. You're reversing the direction of the diode. That's the first step. The current is going to be very small. So you replace the microammeter with the milliammeter with a microammeter. Second change. Third change is the real subtle one. Okay, if you leave it like this now, okay, the voltmeter has a very high resistance. The diode has a very high resistance. A large current, or a reasonable current will flow through both of these. So the reading in the milliammeter is the reading for both of them added together, because the current in the milliammeter splits here. So the reading in the milliammeter isn't great. Okay, so we have a problem. So what we do is, watch, okay, we put the voltmeter across the microammeter and the diode. The microammeter and the diode, okay? Now, so what difference does this make? Well, first of all, it makes the reading of the current perfect, because the current flowing through the ammeter is now exactly the same as the current going through the diode. The question is, have you compromised that with the voltage reading? Okay, so the voltage, remember, is the energy needed to drag the charges through the diode. Okay. Now, the diode has a huge resistance. A microammeter has a tiny resistance. Ammeters are small resistance. So therefore, okay, because this is a huge resistance, this is a small resistance, the energy needed to go from here to here is effectively all used in going through the diode, or almost all used. So that's a much better approximation than doing it the other way. So it's worth looking at that on paper again, and I'll go through it again at another time, but just get clear, when you're doing it in reverse bias, you make 1, 2, 3 changes. Okay, you reverse the connections, or you reverse the position, the direction of the diode, you change the milliammeter with a microammeter, and you put the voltmeter across both the microammeter and the diode. They're what you need really for section A. You won't be asked why in section A. The explanation of it is very subtle, very interesting, and will be very much a very hard bit of a section B question. But have a good look at it, try to figure it out, make sure you know what the changes, the 3 changes anyhow. That solves you in section A. And the other thing is just interesting, keeps the brain active. Okay. Now, when we do that, then, okay, this is reverse bias. We have current, we have voltage. The current is now in microamps, and effectively what you get is a very small current. Okay, you get a very small current. Okay, it can break down. Okay, and you get a very large current, and then it goes back to a small current later. That won't be relevant. Okay, I wouldn't imagine. Okay, so don't worry about that. So that's it. That's your experiment IV graph for a diode. Forward bias straightforward. Reverse bias, what you need to know for section A is the 3 changes you make. Also worth remembering why you move the voltmeter across, instead of being across the diode, it's now across the diode and the microammeter. That's one for the H1s. Okay, to put it mildly. Okay, very good.